Okay, we note that this graph is increasing everywhere. It's always going upward. So this graph is strictly increasing. What's this graph doing? Well, it's strictly decreasing. Okay, what does this graph appear to be doing? Well, from these 3 points, it appears that it's always decreasing, so that it's strictly decreasing. However, we haven't plotted all the points. We haven't examined every possibility. Can you prove that this graph and this graph give you an S versus T graph that is always decreasing? Or can you disprove that? So, good question, worth thinking about. Another question, can you change the T versus X graph in such a way that S versus T exhibits both increasing and decreasing behavior, assuming that it doesn't already? Okay, so if you find that the graph doesn't exhibit both increasing and decreasing behavior, then of course it's always decreasing, because it's certainly decreasing from this point to this and this point to this. If that's the case, could you change this graph of T so that that would be the case? Now, another question, let's just take this X versus T graph and this Y versus T graph. Okay, now, here X was the common variable, here T is the common variable, so X is not going to behave over here the way it behaved over here, is it? It's T that's going to behave the way X did, whatever X did, whether it behaved or misbehaved. Okay, so we have this X versus T graph and this Y versus T graph. Now my question is then, if you construct the Y versus X graph, and you certainly can construct the Y versus X graph using the same ideas that we used over here, first of all, what's the graph look like? And second of all, well, certainly you can graph it. Is Y a function of X? Okay? How could you look at the two graphs and tell whether Y is in fact a function of X? Is there a way? What characteristics would the graph have to have in order for Y to be a function of X? And then another idea that occurs to me right here that's worth looking at. How would the shape of the graph change if Y versus T was shrunk so that every point is 3 times as close to the T axis? That means the Y versus T graph would look something like this. Okay, that would be a vertical compression by factor 3 or vertical stretch by factor 1/3. If you know that terminology. If you don't worry about it, but if you do, it's a good thing to be reminded of it. Okay, so how would the graph change, the graph you get down here change if this happened to Y? So how does the stretch or compression of the Y graph affect the Y versus X graph? And what if you stretched or compressed the X graph and kept the Y graph the same? How would that change the graph? There are rules for that, and they're not too difficult to think about and even possibly formulate. Okay, here. Another question. We've just completed a lot of stuff about power functions, and maybe you completed that, and maybe you're seeing this as a standalone file or standalone exercise or activity. But if you are familiar with power functions, what can you say about the graph of Y versus X over here if both X versus T, this function, and the Y versus T function, this function, are both power functions? Okay, so in this case, now this doesn't apply to this because you don't have X versus T and y versus t, obviously. Okay, so I've got this way over here just because that's where I have room, but you want to think about these graphs. These are clearly not power functions. If these were both power functions, what could you conclude about the graph of x versus t?